China just split a mountain in half to build a bridge. The Huajiang Canyon Bridge in Guizhou Province didn't just span a gap, it required carving through solid rock faces on both sides of a gorge so deep the river below sits over 1,600 feet down. This wasn't about building around nature. This was about forcing nature to make room. And what they pulled off in that canyon redefined what's possible when concrete meets stone. But before they could even think about hanging a single cable, they had to solve a problem that had never been solved before. The canyon that rejected every plan. The Huajiang Canyon doesn't just drop, it plunges. 1,627 feet from rim to river. Sheer limestone cliffs on both sides, worn smooth by millions of years of wind and water. The Beipon River cuts through the bottom like a knife wound through the landscape of Guizhou Province. For decades, this canyon kept communities separated. A 10-minute straight-line distance took 4 hours to drive around. Engineers had studied this gap for years. Every conventional bridge design failed before it even reached the drawing board. Suspension bridges need anchor points. The problem? There weren't any. The cliff faces were too vertical, too unstable. You can't just drill into million-year-old limestone and hope it holds when you're planning to hang thousands of tons of roadway across a chasm this wide. The span needed to stretch 4,980 feet across empty air. That's nearly a mile of bridge with nothing underneath it but wind, and a river you'd need binoculars to see clearly. The anchoring system would need to handle tension forces equivalent to the weight of a skyscraper being pulled horizontally, and those forces had to be absorbed by rock that had been cracking and shifting since before humans existed. Traditional foundation methods were useless here. You couldn't build support towers in the middle. The canyon was too deep, the river too violent, and the cost would be astronomical. The bridge had to be a pure suspension design, which meant everything depended on 2 anchor points, one on each side of the canyon, both carved into cliffs that geologists warned might not hold. Then came the surveys. Teams rappelled down the cliff faces, taking core samples every few feet. What they found was worse than expected. The limestone wasn't uniform. Layers of different densities, different strengths. Pockets of empty space where water had dissolved the rock away. Fault lines running through sections they'd planned to use as anchors. The mountain itself was fighting them. The Chinese engineers made a decision that shocked the international bridge building community. They wouldn't work around the mountain's weaknesses. They'd cut straight through to the strong rock beneath. They were going to excavate anchor tunnels deeper into these cliffs than any bridge project had ever attempted. Tunnels that would go so far into the mountain, they'd create entirely new geological structures just to hold the cables. The equipment started arriving in 2013, but what showed up at the canyon rim wasn't what anyone expected. Drilling into the unknown. The machines that rolled up to the Huajiang Canyon weren't designed for bridge construction. They were tunnel boring equipment, the kind you'd use to carve subway systems through bedrock. Except these weren't going horizontal through a mountain, they were going to drill at angles into cliff faces hanging over a 1,600-foot drop. The plan was insane by any conventional standard. On the north side of the canyon, engineers would excavate a tunnel system that penetrated 320 feet into the limestone cliff. On the south side, even deeper, 430 feet into solid rock. These weren't simple holes. These were chambers, galleries, carved into the mountain where massive anchor blocks would be installed to grip the main suspension cables. The entire weight of the bridge would transfer through steel cables into concrete blocks buried inside these mountains. The drilling started on the North Cliff in January 2014. The first challenge hit immediately. The limestone here wasn't just layered, it was fractured in ways the core samples hadn't fully revealed. As drill heads bit into the rock face, entire sections would splinter. Cracks would race outward from the drilling point, spiderwebbing through the stone. They were essentially performing surgery on a cliff that wanted to fall apart. Every meter deeper revealed new problems. Water. Underground streams they hadn't mapped were flowing through the limestone. When drilling punched into these hidden channels, water would blast out under pressure, flooding the excavation site and destabilizing the rock around it. The teams had to stop, pump out thousands of gallons, then inject grout into the fractured stone just to make it solid enough to continue. Then the drill bit started breaking. The limestone had patches of silica, essentially quartz, embedded throughout, sections of rock that were harder than the tungsten carbide cutting heads. Bits that should have lasted weeks were shattering in days. The project burned through drill heads faster than they could be replaced. Each broken bit meant stopping work, extracting the equipment, replacing components, and starting over. Days lost, budget hemorrhaging. But the real nightmare was alignment. These tunnels had to be perfect. The anchor chambers on both sides of the canyon needed to align with millimeter precision so the suspension cables would hang at exact angles. Drilling into a cliff face at a compound angle angled down and angled inward with that level of accuracy had never been done at this scale. GPS didn't work inside solid rock. Laser guidance systems kept losing calibration as the mountain shifted from the drilling vibrations. 3 months in, they hit a void. A cavity in the limestone the size of a bus, right where the main anchor chamber was supposed to be. The drill punched through and just dropped into nothing. The entire excavation plan for the North Anchor was now useless. That void meant the rock around it was structurally compromised. They couldn't anchor anything there. The engineers had two choices: abandon the site and move the entire bridge location, or go deeper. They went deeper. Another 100 feet into the cliff, past the compromised zone, into older, denser limestone that had fewer fractures. It meant redesigning the anchor system. It meant more drilling, more time, more money disappearing into a hole in a mountain. By the time they finished excavating the North Anchor tunnel system in September 2014, they'd removed over 40,000 cubic feet of rock. The south side took even longer. The deeper penetration, 430 feet, meant fighting the same battles, but in harder, older stone. More water, more fractures, more drill bits destroyed. But finally, after 19 months of drilling, both mountains had been hollowed out. 2 enormous chambers, carved deep into cliffs that had stood untouched for millennia, now waited for the anchors that would hold up a bridge. And then the engineers realized the hardest part was just beginning: anchoring the impossible. The tunnels were empty, cathedral-sized voids carved into 2 mountains. Now came the part that would either prove the entire project was genius or catastrophic failure: installing anchor systems that could hold forces no bridge anchor had ever been asked to handle. The numbers were terrifying. Each side of the bridge would carry tension forces exceeding 65,000 tons. That's the weight of a naval aircraft carrier being pulled horizontally through steel cables into chambers buried in crumbling limestone. The anchor blocks had to be so over-engineered, so massively constructed, that failure wasn't just unlikely, it was physically impossible. The solution was gravity anchors, massive concrete blocks that would be poured inside the mountain chambers, so heavy that even under maximum cable tension, they couldn't move. The north side anchor block would weigh 92,000 tons. The south side, even heavier, 108,000 tons of reinforced concrete entombed in rock. But you can't just pour concrete into a hole and call it an anchor. The block had to bond with the surrounding limestone. If there was any separation, any gap between concrete and rock, the forces would cause shifting. Shifting meant cable alignment changes. Alignment changes meant catastrophic stress on the bridge deck. The concrete and mountain had to become one continuous structure. They started with rock bolts, thousands of them. Steel rods, each one 20 to 30 feet long, drilled deep into the chamber walls at precise angles. These bolts would be embedded in the concrete pour, creating a mechanical interlock between the anchor block and the mountain itself. The installation took months. Drilling, hammering, testing each bolt's grip strength. A single weak bolt could create a failure point under load. Then came the reinforcement cage. Steel rebar assembled into a 3-dimensional grid so dense you could barely see through it. This wasn't normal bridge rebar. These were thick steel bars, bundled and welded into geometric patterns calculated to distribute tension forces evenly throughout the concrete mass. The cage weighed thousands of tons by itself. Getting it positioned inside the mountain chamber, suspended in exactly the right location, required rigging systems normally used for offshore oil platforms. The concrete pour on the North Anchor started in March 2015. This wasn't concrete you'd use for a building foundation. This was high-performance mixed with additives that would make it stronger than the limestone surrounding it. The pour had to be continuous, no cold joints, no stopping. Cold joints create weakness planes. Under the forces this anchor would face, a cold joint would fracture. They poured for 68 hours straight. Concrete trucks lined up for miles, feeding an endless stream of material into the mountain. Pumps pushed the concrete through pipes into the chamber, filling it from the bottom up. The chemical reaction from that much concrete curing at once generated heat like a furnace. Internal temperatures spiked above 140 degrees Fahrenheit, too hot, and the concrete would crack as it cooled. They had to run cooling pipes through the pour, circulating ice water to control the temperature. 3 weeks later, they did it again on the south side. 108,000 tons poured into a mountain. The logistics alone were staggering. Over 45,000 truckloads of concrete delivered to a cliff edge in one of the most remote parts of Guizhou Province. And then they waited. Concrete takes time to cure, to reach full strength. For blocks this massive, it would take months before they could even think about attaching cables. During that time, sensors embedded throughout the anchor blocks monitored stress, temperature, and any microscopic movement. The mountains were under surveillance. By August 2015, the anchor blocks had cured. Load tests began. Hydraulic jacks applied force to embedded test cables, pulling with thousands of tons of tension. The engineers watched the sensors, looking for any sign of movement, any crack formation, any indication the anchors might fail. The blocks didn't move, not a millimeter. The mountains were ready. But building the anchors was only half the battle now. They had to span the canyon itself, threading steel across the void. The canyon waited. 1,600 feet of empty air between two mountains that had been cut open and filled with concrete. Now came the moment that would define whether this entire project was possible. Stringing the main suspension cables across a gap so wide you couldn't see details on the other side without binoculars. Traditional suspension bridge construction uses a pilot cable system. You shoot a small line across first, then use it to pull progressively larger cables until you can haul the main suspension cables into position. But the Huajiang Canyon presented a problem no one had solved before. The span was 4,980 feet, nearly a mile. The cliffs were 1,600 feet high. Wind screamed through that gap at speeds exceeding 60 miles per hour on calm days. You couldn't just shoot a cable across and hope it landed. The Chinese engineers brought in a drone, not a small recreational quadcopter, a heavy-lift industrial drone capable of carrying a payload across the canyon. In October 2015, that drone made the first crossing. It carried a thin pilot rope, essentially fishing line made of high-strength polymer. Flying against canyon winds that tried to smash it into the cliff faces, the drone made the crossing in 18 minutes. The first physical connection between both sides of the Huajiang Canyon in geological history. That thin line became a rope. The rope became a cable. The cable became a pulling system. Over the following weeks, progressively thicker steel cables were hauled across the gap using the pilot line. Each crossing took hours. Each new cable had to fight wind that tried to swing it into the canyon walls. Teams on both sides coordinated through radio, adjusting tension, controlling the pull speed, watching for any snags. By December, they had the pull cables in place. Now came the main event. The suspension cables themselves, the actual structural elements that would hold the bridge deck. Each main cable was just over 3 feet in diameter, composed of thousands of individual steel wires bundled together. Each cable weighed over 2,000 tons, and they needed 2 of them. These cables couldn't be built on the ground and lifted into place. They were too heavy, too long, too flexible. They had to be constructed in the air, wire by wire, using a technique called cable spinning. A spinning wheel, basically a large pulley system, would carry individual wires back and forth across the canyon, laying them parallel to each other. After thousands of trips, those individual wires would be compacted and bound together into the final cable. The spinning operation started in January 2016. The wheel made its first trip across the canyon, unreeling a single steel wire as it traveled. One wire, 4,980 feet long. When it reached the far side, it looped around a pulley and came back. 2 wires now spanned the canyon. The wheel went again, and again, and again. For 5 months, that wheel ran continuously, across the canyon in wind that sometimes halted operations for days. Each wire had to maintain exact tension. Too loose, and it would sag incorrectly. Too tight, and it would stress the anchor system prematurely. Sensors monitored every wire's tension in real time. The wires began forming visible bundles. What started as thin lines you could barely see from the canyon rim grew into thick rope-like structures suspended in the air. Watching the cables grow day by day was like watching biology, in reverse, individual cells accumulating into tissue, tissue into organs, organs into a structure that would support life. But nature wasn't cooperating. In March 2016, a storm system moved into Guizhou that brought winds exceeding 75 miles per hour through the canyon. The partially completed cables, now several hundred tons of steel hanging in the air, began to oscillate. The wires whipped and twisted, creating wave patterns that traveled the length of the span. The entire cable bundle swung in an arc 12 feet wide at the center point. Work stopped for 8 days until the storm passed. When engineers inspected the cables, they found wire damage. Individual strands had abraded against each other during the oscillation, creating weak points. Those damaged wires had to be cut out and replaced. Weeks of work erased by a single storm. By June 2016, both main cables were complete. 37,000 individual wires compacted into 2 massive bundles, each one anchored into mountains and spanning a canyon that had never been crossed at this height. The cables hung in perfect catenary curves, the natural shape formed by a flexible cable under its own weight. Those curves would be the skeleton that held everything else. Now they just had to hang a roadway from them, suspending a highway in the sky. 2 steel cables hung across the Huajiang Canyon. Now, engineers had to do something that seemed to defy physics. Hang a 4-lane highway from them, over 1,600 feet above a river, without any support underneath. The bridge deck would stretch 4,980 feet and weigh over 18,000 tons. That's the equivalent of suspending a 12-story building horizontally in mid-air using only cables. Every pound of that weight would transfer through vertical suspender cables into the main cables, then into the anchor blocks buried in the mountains. The engineering tolerance for error was 0. Construction started from both cliff edges simultaneously in July 2016. The deck wasn't one continuous piece. It couldn't be. It was modular. Individual steel and concrete sections, each one weighing roughly 60 tons, prefabricated off-site and trucked to the canyon. These sections would be lifted into position, connected to suspender cables, then joined together piece by piece until they met in the middle. The lifting system was a feat by itself. Mobile cranes couldn't reach out over the canyon far enough. Instead, engineers installed a cable-stayed lifting rig that ran along the main suspension cables. Think of it as a construction platform that could slide along the cables like a bead on a string, carrying deck sections out over the void. The first deck section went up on the north side in August. 60 tons of steel and concrete, lifted 200 feet vertically, then swung out over the canyon edge. It hung there, suspended by temporary cables, swaying in the wind like a massive pendulum. Workers on the platform had to wait for the oscillation to dampen before they could safely attach the permanent suspender cables and lock the section into position. Every section followed the same terrifying process: lift, swing out, wait for stability, attach suspenders, lock into the previous section. The connections between deck sections had to be perfect bolt holes aligned to within a 1/16 of an inch, despite wind constantly moving both pieces. Workers were doing precision mechanical work while standing on platforms hanging over a 1,600-foot drop. Then winter hit. In December 2016, temperatures in the canyon dropped below freezing. Ice formed on the cables. The steel deck sections contracted in the cold, changing their dimensions slightly. Bolt holes that aligned perfectly in warm weather no longer matched up. Workers had to use hydraulic jacks to compress or expand sections by fractions of an inch just to get bolts through. Wind remained the constant enemy. Canyon winds didn't blow steadily, they gusted. A deck section would be hanging stable one moment, then a gust would hit and swing it 6 feet sideways. In January 2017, a section broke free from its lifting cables during a gust. 60 tons of steel swung wildly on its suspender cables before workers could stabilize it with guide ropes. No one was hurt, but the section had twisted during the swing. It took 2 days to carefully rotate it back into alignment. The deck sections crept toward each other from both sides. By April 2017, the gap between them had shrunk to less than 200 feet. The final section, the closure section, was the most critical. Both halves of the bridge deck had been built independently, and despite all the precision engineering, there were tiny accumulated errors. The closure section had to account for every millimeter of misalignment. They fabricated 3 different closure sections with slightly different dimensions. When the gap was finally measured precisely in early May, engineers selected the section that would fit on May 19, 2017. That final 60-ton piece was lifted into position. It didn't fit. The bolt holes were off by 3/8 of an inch. Workers spent 14 hours using hydraulic equipment to nudge the entire north side of the bridge deck. Thousands of tons of structure, those 3/8 of an inch. At 11:47 p.m., the bolts slid through. The Huajiang Canyon Bridge deck was continuous, but a connected deck wasn't a finished bridge. They still had to pave it, install safety barriers, run electrical systems, and test whether this thing could actually handle traffic. The final test. The bridge was built. Now it had to prove it wouldn't kill anyone. In September 2017, engineers loaded the deck with 200 fully loaded dump trucks. 4,000 tons of weight distributed across the span, more than any traffic scenario would ever produce. They parked them in patterns designed to create maximum stress on the suspension system. The deck deflected downward 31 inches at the center point, exactly what the computer models predicted. The main cables stretched by fractions of an inch, well within safety margins. The anchor blocks inside the mountains registered 0 movement. The bridge had absorbed forces equivalent to a skyscraper's weight without flinching. On December 29, 2017, the Huajiang Canyon Bridge opened to traffic. 4 lanes of highway suspended 1,627 feet above the Beipon River. The drive that used to take 4 hours around the canyon now took 90 seconds straight across. China didn't just build a bridge over a canyon. They carved into 2 mountains, buried 100,000 tons of concrete inside solid rock, spun cables across a mile of empty air, and hung a highway where nothing had ever existed before. The Huajiang Canyon isn't split, it's conquered.